In geometry, curvilinear coordinates are a coordinate system for Euclidean space in which the coordinate lines may be curved. These coordinates may be derived from a set of Cartesian coordinates by using a transformation that is locally invertible at each point. This means that one can convert a point given in a Cartesian coordinate system to its curvilinear coordinates and back. The name curvilinear coordinates, coined by the French mathematician Lamé, derives from the fact that the coordinate surfaces of the curvilinear systems are curved. Well-known examples of curvilinear coordinate systems in three-dimensional Euclidean space are Cartesian, cylindrical and spherical polar coordinates. A Cartesian coordinate surface in this space is a plane. For example, z equals 0 defines the xy plane. In the same space, the coordinate surface r equals 1 in spherical polar coordinates is the surface of a unit sphere, which is curved. The formalism of curvilinear coordinates provides a unified and general description of the standard coordinate systems. Curvilinear coordinates are often used to define the location or distribution of physical quantities which may be, for example, scalars, vectors, or tensors. Mathematical expressions involving these quantities in vector calculus and tensor analysis can be transformed from one coordinate system to another, according to transformation rules for scalars, vectors, and tensors. Such expressions then become valid for any curvilinear coordinate system. Depending on the application, a curvilinear coordinate system may be simpler to use than the Cartesian coordinate system. For instance, a physical problem with spherical symmetry defined in A3 is usually easier to solve in spherical polar coordinates than in Cartesian coordinates. Equations with boundary conditions that follow coordinate surfaces for a particular curvilinear coordinate system may be easier to solve in that system. One would for instance describe the motion of a particle in a rectangular box in Cartesian coordinates, whereas one would prefer spherical coordinates for a particle in a sphere. Spherical coordinates are one of the most used curvilinear coordinate systems in such fields as earth sciences, cartography, and physics, and engineering. Orthogonal curvilinear coordinates in 3D equals coordinates, basis, and vectors equals. For now, consider 3D space. A point P in 3D space can be defined using Cartesian coordinates, equivalently written, or in another system, as shown in Fig. 1. The latter is a curvilinear coordinate system, and are the curvilinear coordinates of the point P. The surfaces q1 equals constant, q2 equals constant, q3 equals constant are called the coordinate surfaces. And the space curves formed by their intersection in pairs are called the coordinate curves. The coordinate axes are determined by the tangents to the coordinate curves at the intersection of three surfaces. They are not in general fixed directions in space, which happens to be the case for simple Cartesian coordinates. A basis whose vectors change their direction and/or magnitude from point to point is called local basis. All bases associated with curvilinear coordinates are necessarily local. Basis vectors that are the same at all points are global bases, and can be associated only with linear or affine coordinate systems. The relation between the coordinates is given by the invertible transformation functions. The point P can be written as a position vector r in Cartesian coordinates, where x, y, z are the coordinates of the position vector with respect to the standard basis vectors x, I, is. Note, for this article E is reserved for the standard basis and B is for the curvilinear basis. However, in a general curvilinear system, there may well not be any natural global basis vectors. Instead, we note that in the Cartesian system, the standard basis vectors can be derived from the derivative of the location of point P with respect to the local coordinate. We can apply the same derivatives to the curvilinear system locally at point P to determine a system of basis vectors specific to location P. We define. These may not have unit length, and may also not be orthogonal. In the case that they are orthogonal at all points where the derivatives are well defined, we define the Lamé coefficients by, and the curvilinear orthonormal basis vectors by. It is important to note that these basis vectors may well depend upon the position of P. it is therefore necessary that they are not assumed to be constant over a region. In general, curvilinear coordinates allow the generality of basis vectors not all mutually perpendicular to each other, and not required to be of unit length, they can be of arbitrary magnitude and direction. The use of an orthogonal basis makes vector manipulations simpler than for non-orthogonal. However, some areas of physics and engineering, particularly fluid mechanics and continuum mechanics, require non-orthogonal bases to describe deformations and fluid transport to account for complicated directional dependencies of physical quantities. A discussion of the general case appears later on this page. Vector calculus equals differential elements, since the total differential change in R is. So scale factors are. They can also be written for each component of R. However, this designation is very rarely used, largely replaced with the components of the metric tensor GIC. Covariant and contravariant bases equals. Spatial gradients, distances, time derivatives and scale factors are interrelated within a coordinate system by two groups of basis vectors. Consequently, a general curvilinear coordinate system has two sets of basis vectors for every point, B1, B2, B3 is the covariant basis, and B1, B2, B3 is the contravariant basis. Note that B1 AB1 equals 1, and the same result holds for directions 2 and 3. The covariant and contravariant basis vectors types have identical direction for orthogonal curvilinear coordinate systems, but as usual have inverted units with respect to each other. A vector V can be specified in terms either basis, that is. Using the Einstein summation convention, the basis vectors relate to the components by and, where G is the metric tensor. A vector can be specified with covariant coordinates or contravariant coordinates. From the above vector sums, it can be seen that contravariant coordinates are associated with covariant basis vectors, and covariant coordinates are associated with contravariant basis vectors. A key feature of the representation of vectors and tensors in terms of indexed components and basis vectors is invariance in the sense that vector components which transform in a covariant manner are paired with basis vectors that transform in a contravariant manner. Covariant basis equals. Constructing a covariant basis in one dimension. Consider the one-dimensional curve shown in Fig. 3. At point P, taken as an origin, x is one of the Cartesian coordinates, and q1 is one of the curvilinear coordinates. The local basis vector is b1 and it is built on the q1 axis which is a tangent to that coordinate line at the point P. The axis q1 and thus the vector b1 form an angle I plus or minus with the Cartesian x-axis and the Cartesian basis vector e1. It can be seen from triangle PAB that where e1, b1 are the magnitudes of the two basis vectors, that is, the scalar intercepts pb and pa. Note that pa is also the projection of b1 on the x-axis. However, this method for basis vector transformations using directional cosines is inapplicable to curvilinear coordinates for the following reasons: by increasing the distance from P, the angle between the curved line q1 and Cartesian axis x increasingly deviates from I plus or minus. At the distance pb the true angle is at which the tangent at point C forms with the x-axis and the latter angle is clearly different from I plus or minus. The angles that the q1 line and that axis form with the x-axis become closer in value the closer one moves towards point P and become exactly equal at P. Let point E be located very close to P, so close that the distance PE is infinitesimally small. Then PE measured on the q1 axis almost coincides with PE measured on the q1 line. At the same time, the ratio PD-PE becomes almost exactly equal to cos I plus or minus. Let the infinitesimally small intercepts PD and PE be labeled, respectively, as dx and dq1. Then, thus, the directional cosines can be substituted in transformations with the more exact ratios between infinitesimally small coordinate intercepts. It follows that the component of b1 on the x-axis is if key equals key, x1, x2, x3, and xi equals xi, q1, q2, q3, are smooth functions. The transformation ratios can be written as and. That is, those ratios are partial derivatives of coordinates belonging to one system with respect to coordinates belonging to the other system. Constructing a covariant basis in 3 dimensions, doing the same for the coordinates in the other 2 dimensions, B1 can be expressed as. Similar equations hold for B2 and B3 so that the standard basis E1, E2, E3 is transformed to a local basis B1, B2, B3 by the following system of equations. By analogous reasoning, one can obtain the inverse transformation from local basis to standard basis. Jacobian of the transformation, the above systems of linear equations can be written in matrix form using the Einstein summation convention as. This coefficient matrix of the linear system is the Jacobian matrix of the transformation. These are the equations that can be used to transform a Cartesian basis into a curvilinear basis, and vice versa. In 3 dimensions, the expanded forms of these matrices are. In the inverse transformation, the unknowns are the curvilinear basis vectors. For any specific location there can only exist one and only one set of basis vectors. This condition is satisfied if and only if the equation system has a single solution. From linear algebra, a linear equation system has a single solution only if the determinant of his system matrix is non-zero. Which shows the rationale behind the above requirement concerning the inverse Jacobian determinant. Generalization to n dimensions, the formalism extends to any finite dimension as follows. Consider the real Euclidean n-dimensional space, that is Rn equals Ra, Ra. Where R is the set of real numbers and A denotes the Cartesian product, which is a vector space. The coordinates of this space can be denoted by x equals. Since this is a vector, it can be written as where E1 equals, E2 equals, E3 equals. N equals is the standard basis set of vectors for the space Rn, and I equals 1, 2. N is an index labeling components. Each vector has exactly one component in each dimension and they are mutually orthogonal and normalized. More generally, we can define basis vectors B so that they depend on Q equals, that is they change from point to point, B equals B, Q. In which case to define the same point x in terms of this alternative basis, the coordinates with respect to this basis phi also necessarily depend on x also, that is y equals phi, x. Then a vector v in this space, with respect to these alternative coordinates and basis vectors, can be expanded as a linear combination in this basis. The vector sum that describes v in the new basis is composed of different vectors, although the sum itself remains the same. Equals transformation of coordinates equals, from a more general and abstract perspective, a curvilinear coordinate system is simply a coordinate patch on the differentiable manifold n that is diffeomorphic to the Cartesian coordinate patch on the manifold. Note the 2 diffeomorphic coordinate patches on a differential manifold need not overlap differentiably. With this simple definition of a curvilinear coordinate system, all the results that follow below are simply applications of standard theorems in differential topology. The transformation functions are such that there's a one-to-one relationship between points in the old and new coordinates, that is, those functions are bijections, and fulfill the following requirements within their domains. Vector and tensor algebra in 3-dimensional curvilinear coordinates. Note, the Einstein summation convention of summing on repeated indices is used below. Elementary vector and tensor algebra in curvilinear coordinates is used in some of the older scientific literature in mechanics and physics and can be indispensable to understanding work from the early and mid-1900s, for example the text by Green and Zerner. Some useful relations in the algebra of vectors and second-order tensors in curvilinear coordinates are given in this section. The notation and contents are primarily from Ogden, Nuddy, Simmons, Green and Zerner, Barsa and Wichert, and Kylot. Tensors in curvilinear coordinates equals, a second-order tensor can be expressed as where denotes the tensor product. The components are called the contravariant components, Cj the mixed right covariant components, Cj the mixed left covariant components, and sig the covariant components of the second-order tensor. The components of the second-order tensor are related by equals the metric tensor in orthogonal curvilinear coordinates equals. At each point, one can construct a small line element dx, so the square of the length of the line element is the scalar product dx a eurocent dx and is called the metric of the space, given by the following portion of the above equation. Is a symmetric tensor called the fundamental tensor of the Euclidean space in curvilinear coordinates. Indices can be raised and lowered by the metric relation to Lamé copyright coefficients, defining the scale factors high by gives a relation between the metric tensor and the Lamé copyright coefficients. Note also that where h are the Lamé copyright coefficients. For an orthogonal basis we also have example. Polar coordinates. If we consider polar coordinates for A2, note that r, I, are the curvilinear coordinates, and the Jacobian determinant of the transformation A is r. The orthogonal basis vectors are BR equals, B equals. The scale factors are HR equals 1 and high equals r. The fundamental tensor is G11 equals 1, G22 equals R2, G12 equals G21 equals 0. Equals the alternating tensor equals, in an orthonormal right-handed basis, the third-order alternating tensor is defined as. In a general curvilinear basis the same tensor may be expressed as. It can also be shown that equals Christoffel symbols equals, Christoffel symbols of the first kind, where the comma denotes a partial derivative. To express IIJK in terms of gauge we note that since using these to rearrange the above relations gives Christoffel symbols of the second kind. This implies that other relations that follow are equals vector operations equals vector and tensor calculus and three-dimensional curvilinear coordinates. Note, the Einstein summation convention of summing on repeated indices is used below. Adjustments need to be made in the calculation of line, surface and volume integrals. For simplicity, the following restricts to three dimensions and orthogonal curvilinear coordinates. However, the same arguments apply for n-dimensional spaces. When the coordinate system is not orthogonal, there are some additional terms in the expressions. Simons, in his book on tensor analysis, quotes Albert Einstein saying, "The magic of this theory will hardly fail to impose itself on anybody who has truly understood it. It represents a genuine triumph of the method of absolute differential calculus, founded by Gauss, Riemann, Ricci, and Levi Civita. Vector and tensor calculus and general curvilinear coordinates is used in tensor analysis on four-dimensional curvilinear manifolds in general relativity, in the mechanics of curved shells, in examining the invariance properties of Maxwell's equations which has been of interest in metamaterials and in many other fields. Some useful relations in the calculus of vectors and second-order tensors in curvilinear coordinates are given in this section. The notation and contents are primarily from Ogden, Simons, Green and Zerner, Barsa and Wichert, and Keilert. Let I equals I, x, be a well-defined scalar field and V equals V, x, a well-defined vector field, and I1, I2 be parameters of the coordinates. Equals geometric elements equals integration equals differentiation equals. The expressions for the gradient, divergence, and Laplacian can be directly extended to n dimensions, however the curl is only defined in 3D. The vector field B is tangent to the key coordinate curve and forms a natural basis at each point on the curve. This basis, as discussed at the beginning of this article, is also called the covariant curvilinear basis. We can also define a reciprocal basis, or contravariant curvilinear basis, B. All the algebraic relations between the basis vectors, as discussed in the section on tensor algebra, apply for the natural basis and its reciprocal at each point x. Fictitious forces in general curvilinear coordinates. An inertial coordinate system is defined as a system of space and time coordinates x1, x2, x3, dt in terms of which the equations of motion of a particle free of external forces are simply d2xj dt2 equals 0. In this context, a coordinate system can fail to be a Euro initiale Euro either due to non-straight time axis or non-straight space axis. In other words, the basis vectors of the coordinates may vary in time at fixed positions, or they may vary with position at fixed times, or both. When equations of motion are expressed in terms of any non-inertial coordinate system, extra terms appear, called Christoffel symbols. Strictly speaking, these terms represent components of the absolute acceleration, but we may also choose to continue to regard d2xj dt2 as the acceleration and treat the extra terms as if they were forces, in which case they are called fictitious forces. The component of any such fictitious force normal to the path of the particle and in the plane of the path the Euro unregistered trademark S curvature is then called centrifugal force. This more general context makes clear the correspondence between the concepts of centrifugal force in rotating coordinate systems and in stationary curvilinear coordinate systems. For a simple example, consider a particle of mass m moving in a circle of radius r with angular speed w relative to a system of polar coordinates rotating with angular speed w. The radial equation of motion is mr Euro equals F plus Mr. W plus W, 2. Thus the centrifugal force is Mr times the square of the absolute rotational speed A equals W plus W of the particle. If we choose a coordinate system rotating at the speed of the particle, then W equals A and W equals 0, in which case the centrifugal force is Mr A2, whereas if we choose a stationary coordinate system we have W equals 0 and W equals A, in which case the centrifugal force is again Mr A2. The reason for this equality of results is that in both cases the basis vectors at the particular Euro unregistered trademark S location are changing in time in exactly the same way. Hence these are really just two different ways of describing exactly the same thing, one description being in terms of rotating coordinates and the other being in terms of stationary curvilinear coordinates, both of which are non-inertial according to the more abstract meaning of that term. When describing general motion, the actual forces acting on a particle are often referred to the instantaneous osculating circle tangent to the path of motion, and this circle in the general case is not centered at a fixed location, and so the decomposition into centrifugal and Coriolis components is constantly changing. This is true regardless of whether the motion is described in terms of stationary or rotating coordinates. See also, covariance and contravariance, Introduction to the Mathematics of General Relativity, Orthogonal Coordinates, Frenata Euro-Serret Formulas, Covariant Derivative, Tensor Derivative, Curvilinear Perspective, Dal in Cylindrical and Spherical Coordinates. References. Further reading. External links, planetmath.org Derivation of unit vectors in curvilinear coordinates, MathWorld's page on curvilinear coordinates, Professor Abranon's e-book on curvilinear coordinates, Wikiversity, Introduction to Elasticity Tensors The Divergence of a Tensor Field Wikiversity, Introduction to Elasticity Tensors.